You instantly recognize this line, right? In space, no one can hear you scream. It's the iconic tagline from the 1979 sci-fi classic Alien. And, from a strictly biological standpoint, it hits the nail on the head. Because there's zero air in space, there is absolutely nothing to conduct the mechanical sound waves created by our vocal cords. If you were floating out there without a helmet, no one would hear a thing. But here's the twist. While space is a vacuum, scientists have recently had a massive paradigm shift. As it turns out, we actually can hear the universe. We just had to figure out exactly how to listen.
Okay, let's dive into this comparison to see how that works. Down here on Earth, we rely on mechanical waves. Like when you speak, you compress air molecules, which bump into their neighbors and pass that vibration all the way into someone's ear. But deep space, it just doesn't have enough molecules for that. Instead, it uses electromagnetic plasma waves. See, while space looks completely empty, it's actually filled with this highly conductive, ionized gas called plasma. And in this plasma, particles are constantly interacting over vast distances through magnetic and electric fields. So instead of using mechanical pressure, the universe ripples with electromagnetic waves. Mind-blowing, right?
Now you might be wondering, how do we actually hear those electromagnetic waves? Well, that brings us to this incredibly cool process on screen, audification. This is the direct conversion of wave-like data into frequencies that fall right within human hearing. Scientists take specialized instruments on their space probes to record the fluctuating magnetic and electric fields of these plasma waves. And because that data is inherently wave-like, it can literally be converted straight into audio frequencies. They just take the electromagnetic signature, speed it up, or shift it into our hearing range and play it back through standard computer speakers. So we aren't creating some fake synthetic sound here. We are literally eavesdropping on the cosmos.
And the crazy part is, this isn't even a brand new idea. Let's trace the timeline here real quick. NASA was actually thinking about space acoustics decades ago. Way back in 1977, the Voyager probes were launched with plasma wave subsystems specifically built in to listen to their environment. Jump forward to 2012, and Voyager 1 crosses the boundary of our heliosphere, sending back this completely unprecedented data. Then, in 2017, the Cassini probe recorded plasma waves generated right between Saturn and its moon Enceladus, just before NASA intentionally plunged the spacecraft into Saturn's atmosphere.
Let's zoom in on Voyager 1 for a second, because this is wild. This incredible piece of machinery is now over 15 billion miles away from Earth. When it finally broke free of our sun's influence and entered interstellar space back in 2012, its instruments actually captured the vibrations of dense ionized gas rumbling out there in the void. So what did it sound like when they audified it? It produced this eerie, high-pitched whistling noise. The pitch and frequency actually shifted up by nearly a factor of 10. And that specific sound is exactly how astrophysicists proved that Voyager 1 had officially left our solar system.
But hey, we don't even need to travel 15 billion miles to hear the universe. Right here at home, Earth is basically singing to itself. NASA's Van Allen probes have recorded these things called chorus waves. These are magnetic waves surging straight through Earth's plasma, completely driven by intense space storms. And when scientists play this audified data back, you'd think it would sound like some terrifying alien laser, right? But it doesn't. It actually sounds remarkably like this bright, melodic cross between chirping birds and whale song. It's honestly quite beautiful.
Now, what's really interesting about this slide is the shift to sonification. We just talked about audification, which uses the actual wave data. Sonification is a completely different ballgame. It's the process of translating digital data, like the X-ray or optical light captured by a telescope, into musical parameters like pitch and volume. So instead of converting a physical wave, you're essentially taking a visual photograph of a galaxy and mapping it into a musical score. Let's break down the clever, step-by-step process of how telescopes like NASA's Chandra X-ray Observatory and the Hubble actually pull this off. First, they map the vertical position of the light to pitch. So, a star near the top of the image sounds higher than one near the bottom. Makes sense, right? Second, they map the brightness to volume, meaning the more intense the light is, the louder the sound gets. And finally, they assign different musical instruments to different wavelengths of light. For example, X-rays might get played by brass instruments, optical light by strings, and infrared by woodwinds. They are quite literally turning multi-layered images of nebulas into full-blown symphonies.
Okay, but today we promised you terrifying sounds, didn't we? So let's leave the symphonies behind and travel 240 million light-years away from Earth. We are going deep into the abyss to visit the supermassive black hole located right at the center of the Perseus Galaxy Cluster. And what scientists found here completely shattered that whole public misconception that space is always a silent vacuum.
To understand why this specific black hole is so special, we have to look at its neighborhood. See, unlike the empty vacuum of deep space, a galaxy cluster like Perseus contains hundreds of galaxies that are enveloped in massive clouds of hot gas. We're talking gas that reaches 180 million degrees Fahrenheit. And this incredibly dense, superheated gas actually provides a physical medium, meaning, unlike those electromagnetic waves we discussed earlier, the Perseus cluster allows real, physical sound waves, actual pressure waves to ripple outward from the black hole. And this brilliantly illustrates the sheer, mind-boggling scale of the cosmos. As this black hole essentially burps and interacts with that surrounding hot gas, it emits a measurable physical sound wave. Astronomers actually mapped the distance between these ripples and discovered the black hole is effectively singing a note. Specifically, it's a B-flat. But here's the catch.
It is singing that note a staggering 57 octaves below middle C. It's a frequency so incredibly deep, so impossibly low, that it is completely and utterly inaudible to human ears.
So what does this all mean? Well, what happens when you try to scale up the groan of a supermassive black hole so a human can actually hear it? To bring that B-flat into our auditory range, NASA scientists had to extract the sound waves and scale the frequency up by 57 and 58 octaves. That means they amplify the pitch by 144 quadrillion to 288 quadrillion times its original frequency. Just take a second and let that number sink in. Quadrillions.
And the resulting sound? Oh man, it is pure nightmare fuel. If you've ever heard the audio clip released by NASA, you know exactly what I'm talking about. It doesn't sound like some crisp, pleasant musical note. No way. It's been described as a haunting ghost or like a deep, heavy, creaky door being repeatedly opened in the dark. It's this low-pitched, guttural, terrifying groaning sound. It is literally the sound of a supermassive cosmic entity banging on the fabric of space like a giant mallet on a drum.
To truly grasp how unique this is, let's compare Perseus to another heavyweight, the famous black hole Messier 87, or M87. Just look at the difference in their source material here. Perseus is an audification of actual physical pressure waves traveling through hot gas, which is what gives us that haunting, low-pitched groan. M87, on the other hand, is a sonification. It's light, X-rays, and radio waves mapped to instruments. Because of that, M87 sounds like pleasant, ambient music with these really light, tinkling chimes. It perfectly highlights how the specific type of data scientists use yields wildly different auditory experiences for us.
Part 1. Psychoacoustics. Why do space sounds terrify us? So the crucial point here is when we hear the Perseus black hole or the eerie whistling of solar winds, why is our immediate gut instinct to feel totally creeped out? Well, it all comes down to psychoacoustics. This is the study of sound perception and how specific audio features trigger these deep, automatic neurological and biological responses inside us. There are three main triggers at play when we listen to the cosmos: acoustic roughness, infrasound, and unpredictability. These three factors combine to make these alien soundscapes feel profoundly unnerving to the human brain. Let's break each one down. First up on the list is acoustic roughness. This refers to extremely rapid, irregular fluctuations in loudness. Think about it. The sound of a human scream in a horror movie, or a blaring emergency alarm. They aren't smooth, pleasant sounds, right? They are harsh, they're jarring. Research actually shows that this roughness occupies a privileged acoustic niche that completely bypasses our logical brain and directly engages the amygdala, which is the center of our fear circuitry. The inharmonic textures of space plasma waves share this exact same acoustic roughness, which is exactly why our brain immediately interprets them as a signal of danger. The second trigger is infrasound. Now we're talking about incredibly low frequency sounds, anything below 20 hertz. Even though these sounds are often way below the threshold of our conscious hearing, our bodies can still physically feel them. Exposure to infrasound causes physiological unease, a total spike in your stress hormone cortisol, and this inexplicable, creeping sense of dread. Even when NASA scales up those massive pressure waves from the Perseus black hole, the remaining low-frequency components still tap into that deep-seated biological anxiety. You literally feel the black hole groaning right in your chest.
And our third trigger is unpredictability. Human music and nature sounds here on Earth generally follow familiar, predictable, rhythmic, and harmonic patterns. But guess what? The universe absolutely does not care about our musical rules. Space sounds, like the sporadic, random wails of a magnetospheric storm or the strange, stuttering rhythm of a pulsar, they lack any kind of earthly context or resolution. Because our brains just can't predict what's coming next, we can't habituate to the noise. And that keeps our limbic system completely on edge and in a constant state of hyper-alertness.
But why does all of this matter? Like, are scientists really just out here trying to give us goosebumps? Far from it. Listening to space is an absolutely vital scientific tool. By understanding plasma waves, scientists can actually predict space weather, which helps protect our satellites and astronauts from dangerous radiation. Sonification allows us to probe the density of the early universe. But perhaps most importantly, translating visual data into sound completely broadens the field of astrophysics. It makes these incredible discoveries fully accessible to the blind and low vision community. It literally turns complex data into a multi-sensory learning experience for absolutely everyone.
So, as you can see, space is far, far from a silent void. It's this dynamic, echoing theater filled with chorus waves, singing planets, and the 57-octave groans of supermassive black holes. Which leaves us with one final, pretty exciting thought to ponder. As our instruments get better and our space probes travel further and further out into the unknown, what other terrifying or breathtakingly beautiful sounds are just waiting to be uncovered in the dark? Thanks so much for joining me on this explainer, and remember to keep listening to the stars.